1, 2, 3. This video is about characteristics of functions. First, we're going to have domain problems. Find the domain for each of the following three functions. Reminder that a domain are all of the inputs or x values that you can substitute into a function that result in an output or a y value coming out. So the first function is a polynomial function. Polynomial functions, unless there are given domain restrictions, do not have any restrictions. You can substitute any value in for x and there will be a y value that comes out. So the domain of the first function, f of x, is negative infinity to infinity. Number 2, g of x is a rational function, and rational functions have the property where the denominator must not equal 0. If the denominator equals 0, then you have an undefined function which does not have an output. So if we set the denominator equal to 0, we would get x squared equals 9. And then when we take the square root, we get x equals plus or minus 3. So the function cannot have positive or negative 3 substituted in. Therefore, the domain of number 2 would be negative infinity to negative 3 union negative 3 to 3 union 3 to infinity. There are no restrictions on the numerator of a rational function. Third, we have h of x, which is a square root function, a radical function. Radical functions that have an even index, so a square root is like putting a 2 there, or if I had a 4th root or a 6th root, anything that has an even index has the property that the inside must be greater than 0. If the index is odd, like a 3rd root or a 5th root, there would be no such restriction. You can have anything be substituted in. But the square root has a property, so this is an even one. So the square root and the 4th root would have the property that the inside must be greater than or equal to 0. Inside must be greater than or equal to 0. And the reason for that is, let's say I had the square root of negative 1. Well, there are no two real numbers that I can multiply together that end up giving me a negative number. But it would work if there were 3 numbers, like the cubed root of negative 1. I could get negative 1 times negative 1 times negative 1, and that would end up giving me negative 1. So that's why odd ones work and even ones don't. So I have to set 5 plus x greater than 0. So x must be greater than negative 5 to work in the domain. So therefore, the domain of this function is negative 5 to infinity. And actually, I keep doing this, so that's my fault, but the inside must be greater than or equal to 0. So actually, x must be greater than or equal to negative 5, which means that this should actually be a bracket. So negative 5 to infinity is the domain of this function. Let's do a quick vocabulary review. The domain and range of a function are the set of all possible inputs and outputs. Domain we usually call x, and range we usually call y. Local or relative minimum or maximum. Local and relative are used interchangeably. So we could say local minimum or we could say relative minimum, and that would mean the same thing. Now obviously minimum and maximum are different. but minimum would be the low point and maximum would be the high point. So these are the points on a function that have an output value, so that's a y value, that is less than all other points that surround it. So if I draw a graph, this would represent a local minimum because all points in a local surrounding area around it are above that point. And then this point would represent a local max or a relative max because all points that are surrounding it are below it. So this is the highest point in a certain area. The global or absolute minimum or maximum, global or absolute, are used interchangeably. Those are points that are the highest in the entire function over the entire domain. So if I look at this graph, it wouldn't have an absolute minimum or maximum because it appears to go down forever and up forever. So there's no point that's higher than every other point on the entire graph. However, if I restricted this graph in such a way where these are endpoints and I have domain restrictions, what I would see is that if this point, it does look slightly higher than our local max, this would be a global max. But this point does not appear to be lower than this red dot. So this local max would also be a global, this local min would also be a global min. So local and global mins can exist at the same spot. There are some textbooks and math people that think that anytime there's an endpoint that automatically qualifies as a local max or min. So this would be a local min for those people that believe that. And this would be a local max because this point is lower than every point that surrounds it, and this point is higher than every other point that surrounds it. But on the AP exam, they usually won't ask you questions about that for AP Calculus. Increasing, decreasing, and constant intervals. An increasing interval is an interval where as you move to the right, the function is going up. A decreasing interval is as you move to the left, the function is going, or as you move to the right, the function is going down. And constant intervals are as you're moving to the right, the function stays at the same level. Finally, we're going to do all of these questions for this graph. And we'll just give the graph. On another video, we'll talk about the calculator functions for this. But here is the graph of f of x. Here's the graph just as it goes off to negative infinity and infinity. And it has certain values listed and the x-intercepts. And then here is the graph over the specific interval that it talks about from -2 inclusive to 1 exclusive. So 1 is not included, but -2 is. So here's kind of what the graph looks like. If we're looking for the domain, that's pretty clear. That's from -2 to 1. If we want to look for local minimum values, there are 2 of them, because those are the values that are bottom out values. So everything surrounding those that I just highlighted in green, everything surrounding those in a local area is above it. The local maximum would be this value. Then if we're looking at decreasing intervals are intervals where the function is going down. So that would be in purple. Increasing intervals are where the function is moving up. So I'll draw that in whatever this color is. And then we just have to remember that we have this domain restriction. So if I'm looking at where these increasing and decreasing intervals are on this interval, that's kind of what I'm looking at. And then if I'm looking at the range of this function, the domain was clearly -2 to 1. The range of this function is going to be from the very bottom value to the very top value on my interval. So that's going to be, it looks like, -6.012 all the way up to this y value, which is 39. So if I look at all of these things, they're listed here. I have the global max and the global min that are listed here. I have my increasing and decreasing intervals. There were no constant intervals. One other thing to keep in mind is that some mathematicians say that a local max or a local min will always occur at an endpoint. So this would end up being a local maximum. However, this cannot be a local min because this point doesn't exist. Remember that 1 was not included. So because that's the case, this point doesn't exist, and I can't include this point as a global min or max. Even though it's an increasing interval, so it would be in the max category if it was included, I can't include it. One final thing that we want to talk about, everything that I'm starring in purple is an interval. So those only include x values. X values are included in intervals. We don't talk about y values in intervals for relatively obvious reasons, because y values can fluctuate a lot, and you wouldn't really know where you are on the graph. So intervals are only x value intervals, with the exception of range. So range would be an interval of y values, but all other intervals are only x values. And then everything that I'm about to star in whatever this color is are points or ordered pairs. Those are x comma y.